Joseph Lombardo is the Executive Director of the National Computing Center and the Director of the Research Network, and have been doing this since 1997. He's also been a consultant to industry, academia, and government biotech due to his expertise in modeling codes, massively parallel computing, and data management. He is principal investigator on a number of grants. He will be discussing big data.
Well, what I'm going to talk about today is a slightly different perspective. I'm going to cut from the perspective of an executive director of a supercomputing center, which is exciting, but it's also very expensive. So I'm going to be touching on the financial side of this, the corporations that are getting involved and whatnot. So one of the issues today is the next generation sequencing machine. These machines are producing more and more data, and the profiles of them are changing rapidly, so we really need to keep a close eye on them. We're going to be talking about sequencing and workflow, market trends and challenges, target market segments, wants and needs from the researchers, and something brand new. And if you're a computer scientist and you want to talk about this offline at the poster session, I'll be more than happy to do that. It's called zero copy architecture. So it's basically storage that's as fast as RAM in a machine. And then we're going to be talking about collaborations and events, and finally Q&A. So again, IT challenges with next generation sequencers, and that's what I'm looking at as a director. So we have complex storage, complex data management, and complex informatics. Cost of sequencing, as you know, in 14 was less than 1,000. In 2003, it was $3 billion. Genomic, clinical, and pharmaceutical research generates a staggering amount of data. As of 2015, NIH generates 2 petabytes of data a month, and that is only from internal NGS systems. 2 petabytes. The prediction is within 2 years it will be up to 20 petabytes a month, just inside of NIH. And I always like to tell people that big data goes hand in hand with big money. Some of the issues is really the unstructured scientific data overwhelming to legacy systems. Legacy systems are basically just standard systems that are in place today. So they don't really meet the needs of groups like the Nevada Institute for Personalized Medicine, but the industries are changing rapidly. The biggest issue is scale. How fast can we scale? Legacy systems don't scale very well. They scale, Moore's law says every 18 months things double. That's inadequate for this kind of science. Justin had mentioned earlier the 3 V's of data. And he mentioned volume, which is data at rest on a hard drive, which costs money. Data in motion, which we call velocity, and this is stream data, milliseconds to seconds to days to weeks to months. Variety, data in many forms, very complicated, structured, unstructured, text, multimedia, and the V that I like to add, veracity, data in doubt. And data in doubt for medicine is a huge, huge deal. In computer science, we say garbage in, garbage out. So the integrity of the data is really important for us. High throughput sequencing workflow. This next little part is actually out of Broad. So I've kind of taken an example there. I like to call it 3 billion base pairs, 20,000 genomes, 23 chromosomes equal you and me. Now this slide is from Broad. And you can see the circle. It's called workflow. We start with the sample DNA, we extract it. Then it finally gets to the sequencers. Again, I told you the sequencers are going to create all the data. This area is just, the effects, the number of companies that are coming aboard is unreal. You can see the flow here. They show 6 or 7 machines. It's really 3 machines that they have there right now to do the pre-proc sequencing, the sequence assembly, and then the sequence analysis. Now here is a device that's out in the field right now. It's a handheld sequencer. And it's being used at medical clinics, and it's also being used in hospitals. Can it do a full human genome? No. They predict within 3 years it will be doing that. But right now for viruses, it's really useful. Okay, so market trends, where are we going? Increased funding, of course. Ted Stanley's $825 million gift to Broad in 2014, a substantial lift. Commercialization of genetic testing and diagnostics. So we see 23andMe, that's a company that produces a $99 to $199 kit that you can take home. Illumina, of course, Marty's group's working with them. The Oxford Nanopore, that's the device I just showed you a few minutes ago. The completion of the 1,000 Genomes Project for Global Research was accomplished in 2015. 2,500 individuals, 26 different population, and a 100 terabyte data set of analyzed data. The formation of Precision FDA, another government project, open source genomic analysis pipelines, reference data, and analytic processing. We have another RFA that's hit the street. So this is Centers for Common Disease Genomics. $300 million pot of money. So what they expect is 150 to 200,000 individuals will be sequenced. The White House will spend this year $1 billion on cancer research, and a lot of it has to do with the genomics side. For the first time in 2016, our first insurance coverage for genome sequencing and diagnostics, specifically in the cancer area. And we all know that the sequencers are dropping fast. And the handheld one, by the way, I can't find the price on, but I do know you pay for using it. So there's a fee for using it. I think you get the device for free and then you pay a monthly charge. It's a no IBM chip. Now, the groups that are involved in it are part of the solutions. The ones that I picked out here are the people or the groups that are using this zero copy technique. So we have the Institute for Molecular Science, the Institute for Statistical Mathematics, the Goya, we have Kyoto, and we have Osaka. So the Japanese are certainly taking it really seriously. We have the Frederick, which is in Virginia. We have Inova, which is also in Virginia. Gladstone, which is close to the Washington, D.C. area. And TRI, which is out of Australia. We have the National University of Singapore, University of Copenhagen, BioGEMA, and this is really agriculture genomics, but it's one of the larger groups that are doing genomics in ag, and it's based in Europe. And then we have TGAC, which is a very interesting group, and they're out of the UK. But then I'm leaving out the most important group in this area, and that's NIPM. So, what are our problems? Well, challenges are memory constraint and assembling large and complex genomes, bottlenecking the workflow from too many apps and too much data spread across an x86 cluster hardware. What are these big groups using? This is a typical example. 4 SGI UV systems with 44 terabytes of globally shared memory, 4,000 cores and 32 5-core processors, and something really, really important, the Intel non-volatile memory controller. Brand new, just hit the streets. It really makes storage look like RAM. And I think Intel's going to make a lot of money. The primary vendor for all this is SGI. They're using their optimized shared file systems. There's a number of apps that I've put in here, and that's more for the scientists. Solution outcomes provide reliability, efficiency, and leading performance to a diverse set of data and compute-intensive analysis. The researcher's workflow and over time to solution is accelerated by running all on a single system, and that's what I showed you in the flow diagram. And then finally, reduce costs. If we go back to that flow diagram and we looked at those UV systems, the cost for them is about 500,000 rack. So you're looking at about $2 million for that solution that Broad is using right now. But they are very happy with it. Okay, so forecasted in genomics, 22 billion by 2020. Actually, I'm using a really low number. I've seen it up to 48, but I decided to be conservative and go with the 22 billion. We have key targets in this area, and I like this. Next generation sequencing companies. Right now, there are emerging 50 or more of them as we speak. Diagnostic companies, 50 or more as we speak. And these are major companies. These are not mom and pop shops. Big pharma and contract research organizations, CROs, over 50 of them. Higher education and medical research, over 100, and NIPM is one of those right now. Hospitals, 2,000 hospitals. will be using it in the genomics and medical clinics, 4,000. A lot of these see that handheld device as very, very useful and also producing enormous amounts of data. Here's a short list of next-gen sequencing companies. I won't keep it up there very long. Diagnostic companies. This is a short list. There's a website there you can go to learn more about them. Next-gen sequencing markets. These are the companies that will take advantage of the sequencing and the data. I'm giving you a really short list here. There's over 100 of them. I gave you the first 20 or something like that. So I start with digits and go to seed cancer genetics. Wants and needs of our researchers. Less than 25% of life scientists have access to high-performance computing, few of whom have ever used a command line. And what that means is they write standalone programs where they point it to data and the output comes someplace, but they don't actually speak to and command the machine. The kind of nodes that are coming out, again, expensive, but there are all kinds of varieties. We got fat nodes, skinny nodes, large memory nodes, GPUs, FPGAs, and the PHYs, the ARMs, and the solid-state devices that you're all familiar with, and the fastest solid-state is called DSSD, and then again you see the Intel non-volatile memory controller. So what are we really looking for in this area, at least Broad and some of the other big ones, computing and networking a single computing and network infrastructure to support things like HPC, Hadoop, OpenStack, cloud, and rapid movement of terabytes and petabytes. Support for over 50 commercial and open source apps such as R, Python, Perl, and others. Needs. It seems like the need in this community is to get access to zero-copy architecture. It really, really does speed things up. I'm looking into it now. I've been given a system by Intel to play with to see what we think about it. Then I'm going to present some results tomorrow and see how we move forward. We really need uniform standards in programming and code optimization. This is really a big deal. Moving codes from one platform to another is really a nightmare. And we also need compatible, configurable, and scalable single system architecture. So zero copy. I'm not going to talk about this much. It's just getting rid of burst, and it's actually going to go into, right now this is the way it looks. This is what it will look like in about 2 years. And what we will be converging on is a machine that doesn't really distinguish between storage and RAM and compute. It will all be one integrated system. The ones that are using the Broad right now with the UVs and the lights are working really well. Now, collaborations, events that are going on only in this area. They're not specific to genomics, but they are specific to hardware and architecture as it relates to supporting this kind of research. I'm going to go fast. There's one in Mountain View, San Francisco, Copenhagen, Brazil, Dallas. This is the one that I'm going to target. I've told from my colleagues at Johns Hopkins that this is probably the best evidence of what's happening as far as the hardware and networking infrastructure that supports this kind of science. Canada, Philadelphia, Texas, Philadelphia, Germany, Boston, computational biology in Orlando, Dallas, DC, Dallas, Utah, Dallas. So you can see a lot of activity. And this hasn't to do with specifically about the research, it has to do with how we're going to support the research. Finally, we look at big data, scratching our heads, we say questions, and then I'll ask for hands.